So last class we left off. We learned about electron configurations previously. We had learned about magnetic properties for ions. So you can have some possible options. Transition metals in particular can be paramagnetic, meaning that they have unpaired electrons, like in this ferric ion, where it's Fe3+. All of these up spins are uncanceled out. We get +1/2 for each of them, so we've got a total spin of +2.5. And these unpaired electrons can generate a magnetic field because of their spin. So it will be attracted to a magnetic field. The other option is diamagnetic, meaning all the electrons are paired, the di like two directions. So we've got, for an example, a full 3D shell. All of our upspin is canceled out by downspin. There's no net spin. And this will be slightly repelled by a magnetic field. It's not magnetic. And we went over this example with the CO2+ ion, cobalt 2+ ion. We did not yet get to our nitride ion. So for our nitride ion, we need to find nitrogen on the periodic table. It's got 7 electrons. Normally, if we have N3-, how many electrons are we going to have? 10. Each electron has a 1 negative charge. So 3- means 3 extra electrons, since electrons are negatively charged. So N3- has 10 electrons. And so if we do an electron configuration, we can use our shortcut for helium, which arguably takes longer than just writing out 1s2. And then after that, we are in row 2, because that's where nitrogen's found. And so we would be going through lithium and beryllium, and those are in our S block in row 2, so it's 2s. Since we're past it, it's full. It's only 2 wide, so it's 2s2. Then we jump over the gap above our transition metals to boron. And we get to boron, carbon, nitrogen, which is the 3rd spot. So it would be 2p3, but we added 3 more electrons. So instead of 2p3, it's 2p6. So we've got our original 3 that nitrogen always has, and then we have an additional 3 from our 3- charge. The other way we could think about this is if we're looking at the periodic table, if we move 3 spots over to the right for 3 electrons added, it's like we're neon. And so we just fill it in like we're neon. To do the electron configuration, we've got our 2s and our 2p. Our 2s is 2. Our 2p is 6. So we're going to have 1, 2, 3, pair them up, 4, 5, 6. So our 2p is full. You could also know that we've got a full outer shell because we have the same number of electrons as neon, and neon has a complete outer shell, complete n=2 shell. Now that we've got our orbital diagram, is this paramagnetic or is it diamagnetic? It is diamagnetic. All of the electrons are paired. Questions? All right. We had talked about trends in atomic radius. So if it's the neutral atom, if it's the neutral elements, the ones we see on the periodic table, how do the sizes change? And we talked about how effective nuclear charge causes us, when we go left to right, let me just go back to the slides. Effective nuclear charge, we compared nitrogen and argon, and our effective nuclear charge is our number of valence electrons, or total electrons, minus our core electrons. And so for nitrogen, we have an effective nuclear charge of 5+. So the outermost, the valence electrons, are experiencing basically a 5+ charge, a 5+ pull towards the nucleus. When we get over to argon, or anything in the noble gas row, we have an 8+ effective nuclear charge. That's a bigger attractive force, and so it pulls in even more. And so that's why we see a decrease in our size as we move left to right. So moving across a period, we get smaller atomic radii. I think it's often easier if we think of the ways that it increases, so it increases the opposite direction, right to left. And when we move down a column, we're adding shells on, and so obviously it makes sense. We're adding new layers on, it's going to get bigger. We also have similar trend ideas, at least, for our ionic radius. So for the ionic radius, cations are much smaller than neutral atoms. We're primarily thinking of our main group elements here. So with our main group elements, for example, right, sodium or magnesium, sodium and magnesium have 1 or 2 valence electrons in their outermost shell. If we turn sodium into Na+, it strips away completely that outer shell, and now it's like it's neon. So we took a whole outer shell away. That's going to make it drastically smaller. Same idea for magnesium, for boron, for aluminum, any of our cations. We're taking off a complete valence shell. So cations go down an electron shell. It's like we're moving up a row. It's not exactly like we're moving up a row, but it's sort of the same idea as though we're moving up a row. On top of that, we've got higher effective nuclear charge. We haven't changed the number of protons, so we've got added protons compared to like what helium or neon would have, depending on which element we're talking about. Like if we've got potassium is in row 4. When it loses 1 electron, it becomes like argon, but it has 19 protons, and so it would be even smaller, because those protons means higher effective nuclear charge, stronger pulling force, and it's the same idea for all of our cations, our positively charged ions. For our anions are much larger than neutral atoms. So we are adding more electrons. This is usually to complete the shell. Whatever our valence shell is. Since we're adding on extra electrons, we're not adding on a complete shell, but we're filling out the shell. And when we do that, since there's been no change in our nucleus, our effective nuclear charge goes down slightly. It doesn't go down a lot. We haven't changed it probably by whole number increments, because we've just added valence electrons, and so they're all in the same shell. They're not shielding each other to the same degree as our other shielding. But there is some shielding effect going on, and so that causes them to be much larger. We can also compare ionic radius between what we call isoelectronic ions. So iso, meaning basically same, I think it works the same here. And then electronic, we're thinking of as number of electrons, or relating to electrons. So isoelectronic ions are different elements that have the same number of electrons. If we have a series of isoelectronic ions, the ion with the most protons will have the smallest radius. So more protons leads to smaller radius, and this is again because of effective nuclear charge. So looking at a set of ions, we've got S2 minus, Cl minus, K plus, and Ca2 plus. These all have 18 electrons. So they all have the argon electron configuration, since argon has 18 electrons. S2 minus gets bigger because we've added 2 electrons. There's some shielding effect. Chloride gets a little bit bigger. We've added 1 electron, so the shielding effect is slightly less. Potassium and calcium have lost 1 and 2 electrons respectively. So we stripped away their outer shell, but they also have that drastically increased effective nuclear charge because we've got more protons. And so there's more positive charge in our nucleus, and so it shrinks the nucleus, or shrinks the electron shell more. It pulls the electrons in closer. So if they all have the same number of electrons, more protons means smaller radius. Okay, for each of these, choose the larger atom or ion from each pair. All right, we've got one of them is a cation, one's an anion, and then the third is an isoelectronic series. It's just 2 ions, but it's from this series of isoelectronic ions. So between potassium and the potassium ion, which is going to be larger? The neutral one, yes. Potassium, just K, is going to be larger. Does anyone know why? Cations are smaller than the neutral. And they're smaller because they lose their shell. They lose their valence shell. And they have a higher effective nuclear charge. So for potassium, we're stripping away the shell. It becomes basically argon in terms of its electron configuration, but it's got 1 extra proton compared to argon, so it's going to be extra small because of that. On the other hand, we've got fluorine and the fluoride ion, which is going to be larger. Yeah, the fluoride ion is going to be larger. It's got 1 extra electron, and so it basically has the neon configuration, but with only 9 protons. So anions are bigger because we added electrons. There's some shielding even though they're in the same level, and so it results in a lower effective nuclear charge. So they gain electrons, which results in lower ZF, effective nuclear charge. And then we've got calcium, but as a 2+. And we've got chloride as a 1+. Sorry, 1-. So these have argon electron configuration. Which one is going to be larger, the calcium ion or the chloride ion? Ca or Cl? It is going to be chloride. Chloride is larger. They have the same number of electrons, and so the only thing really that's different about them is the number of protons that they have. Chloride has fewer protons. And so it has a lower effective nuclear charge. So it has less pull on valence electrons. So they're not pulled as tightly, they're not squeezing down quite as much, which means that it's larger. The other way that you could think about it is that more protons means a smaller ion, and so calcium would be smaller. That makes chloride bigger. Questions about any of those? All right, another periodic trend that we have is ionization energy. Ionization energy is the energy needed to remove an electron from an atom or an ion in the gaseous state. Ionization energy is always going to be positive. You always have to put energy in to remove an electron. So for M, some metal, if we add in the amount of energy that it takes to do one ionization, we get a 1+ ion, and we get the electron that pops off. If we go from the ion, so starting with M+, we can add the second electron ionization energy, and it goes to a 2+ charge, and this is the other electron that we remove. So the 1 here means that it's the first ionization energy. The 2 here means that it's the second ionization energy. If you took Chem 20, you probably covered ionization energy, but just the first ionization energy. We will also talk a little bit about second and subsequent ionization energies. So it takes energy to remove an electron. Our first ionization energy decreases going down a group. So as we're moving from top to bottom, our ionization energy decreases. So if we look at, we've got a graph here, it's atomic number on the x-axis, so we're just working our way through the periodic table left to right, and jumping down rows. And then our ionization energy here on the y-axis, this is how much energy it takes to do that first ionization. And we've got our alkali metals here on the bottom, we've got our noble gases here on the top. So if we look at our alkali metals, there's a slight trend. It's a little bit subtle, but lithium we can see here is above 500, sodium's about right at 500, potassium's below 500, rubidium's a little lower. And those are all of our alkali metals. So you can see as we're moving down groups, our ionization energy is decreasing. We're adding layers as we move down, and so since the electrons are further away, it's easier to pull them off, or it's easier to knock them off. They're not held as tightly. If we look at our noble gases, we see the same trend. So from helium to neon to argon to krypton to xenon, moving our way down the periodic table, moving down that noble gas group, we can see a very clear trend of ionization energy decreasing. And again, this is because valence electron is farther from the nucleus. It also generally increases across a period. We can say that this is because of effective nuclear charge, and that's probably the most reasonable way to think about it. But we can also think about, we're removing an electron. If we think about the extremes, lithium sodium, potassium, these ions, if they lose one electron, they jump over and they become noble gas configuration, which we know is stable. That's like the target goal for any ion, is to become that noble gas configuration. Noble gases are really stable. If we go to something like fluorine, chloride, bromine, chlorine, any of our enes, right, our halogens, the direction that they are closest to becoming a noble gas is gaining one electron. Ionization energy is removing one electron. That's the wrong direction for them, so they really do not want to do that. And then everything in between kind of follows the same trend. But probably more reasonable to think about it as effective nuclear charge increasing. We've got, as we're moving left to right, we've got protons, so our effective nuclear charge increases, so the electrons are held in more tightly. The electrons are held more strongly. So they're harder to remove. That's why the ionization energy increases. Questions about first ionization energy? So this one increases left to right, bottom to top. How does that compare to atomic size? It's the opposite. So this is the opposite of atomic size. So if you don't want to remember the details, or if you think you're just not going to be able to hold on to the details, a little flashcard with first ionization energy and the increases this way, right in the directions. You can do the same thing for atomic size. That's not to say that you'll get every point that you possibly can if you just memorize the trends that way, but that's a good way to at least get them down. And there's a few that are one direction, and there's a few that are the opposite. If we look at ionization energy, first ionization energy, we can see that it increases left to right. So we can see these bars get slightly taller as we move left to right. They also have the values written on them. Hydrogen is an oddball here, and then it also increases as we move down to up. So radon, xenon, krypton, we can see the energy increasing. Helium has very clearly the highest ionization energy. So based on our periodic trends, let's pick the element that's got the higher first ionization energy. We've got first up tin or iodine. We're looking for higher ionization energy, so SN or I, which is going to have higher first ionization energy. Harder to remove an electron. What direction does iodine want to move? Does it want to lose electron or gain an electron? What's its closest path to becoming a noble gas? Gaining one electron would be faster, right? So losing one electron, moving to the left, would be the wrong direction. Tin is sort of smack dab in the middle. It could gain 4 to become noble gas. It could lose 4 valence electrons to become noble gas. So it's not really as big a deal. So our higher ionization energy is going to be iodine. Ionization energy increases left to right. Because of effective nuclear charge. So iodine is further to the right. It's going to have the higher ionization energy. And then what about calcium and strontium? Which one is going to be harder to remove an electron? What's different between calcium and strontium? They're in the same column. How do calcium and strontium compare? Huh? They're in a different row. What changes with row? Calcium is higher. Calcium is the correct answer here because it's smaller. So our electrons are closer to the nucleus. So since our electrons are closer to the nucleus, they're closer to our positive magnet nucleus, they're going to be harder to remove. For strontium, they're held further away, so they're easier to remove. Our ionization energy increases as we move towards helium, so left to right, bottom to top. And then what about carbon or phosphorus? Which one do we think will be harder to remove an electron from? We've got a guess for phosphorus. So this one's tricky, right? So for ionization energy, it increases as we go up. So in terms of up-down, carbon has a higher ionization energy. It also increases left to right. So phosphorus on the left-right has a higher ionization energy. And so this is one where we would probably just, I don't know, because we've got competing trends. I would guess that the size makes a bigger difference than the increased effective nuclear charge. And, as it turns out, I would be right. So carbon's slightly higher in ionization energy, and it looks like that trend does not always hold. So like if we look at sulfur and bromine, bromine has the higher ionization energy. So it's not a surefire method. That's one that I wouldn't probably give you on an exam. So just based on periodic trends, we can't say definitively that there's a clear higher ionization energy, but we can make a guess. And then what about fluorine or sulfur? Which one's higher ionization energy? We've also got two trends going on with this one. Fluorine. It's definitely fluorine. Fluorine wins in the up-down, right? It's higher ionization energy because it's smaller. It's also further to the right, and ionization energy increases to the right. So it wins on both trends. So it's smaller and it's further right. So it's definitely fluorine. There are some exceptions to the trends in our first ionization energy. So it generally increases from left to right. There's an exception between groups 2A and 3A. For example, boron has a smaller first ionization energy than beryllium. So boron's on the right side of the periodic, the gap for over the transition metals. Beryllium is on the left. Boron is losing a 2p electron. And 2p electrons are higher in energy, therefore less stable, so they're easier to remove. So if we look at orbital diagrams, for beryllium and boron, and I just draw the labels under the lower one. So we've got our 2s and our 2p. And if we look at beryllium, we're going to have a full 2s subshell. For boron, we also have a full 2s, but we've got one electron in our 2p. So if we remove an electron from beryllium, we're breaking up this pair, this matched pair of electrons. If we're removing an electron from boron, we're taking one electron out of this 2p subshell. It's not paired with anything. We're still going to have this intact 2s, and since 2p is higher in energy, it's easier to remove. So we break the pairing, but it's also a difference in higher energy. Other exceptions to our trends in first ionization energy. There's another exception that occurs between our 5A and 6A groups. So our 5A is nitrogen group, and our 6A is the oxygen group. So if we're comparing between nitrogen and oxygen, these are our electron diagrams, or orbital diagrams. For nitrogen, we've got a half-filled shell. So we've got good spin symmetry. They're all in the up direction. So if we remove one, we're taking out, these are all kind of like in resonance, we could sort of think of it. They're all paired up. So if we remove one, we're breaking that pairing. For oxygen, we're removing this one this one paired electron. And removing that brings us to a half-filled shell. And since it's paired, doesn't like to be paired, and we go back to a half-filled shell, half-filled shells are a little bit more stable because of that spin symmetry, or that spin parallelism, whatever we'd call it. So oxygen, slightly lower ionization energy than we might expect. If we go and do additional ionization energies, each additional electron requires more energy. So we've got a little bit of a 3D graph here. We've got comparing sodium and magnesium. Up front, we've got first ionization energy, behind it second, behind that third. And the value is measured in the height here. So if we look at sodium and magnesium, which are right next to each other on the periodic table, sodium has a really low first ionization energy relative to the other bars on the graph. Then the jump to the second ionization energy is huge. Especially if we compare it to magnesium. It's got a bigger first ionization energy, but its second ionization energy isn't very big. And then its third ionization energy is massive. So when we remove the first electron from sodium, sodium has one valence electron. So removing that first electron brings it down to a noble gas configuration, neon. It's got 10 electrons. Then when we go to remove that second ionization, do that second ionization energy, right, it takes a ton because we're taking it out of that full core electron layer. So we're removing one, we can basically think of it as like we're taking an electron from neon at that point. So that's why there's a huge spike. And then there's not quite as big a jump for the third one because we're no longer breaking up a full shell, we're just taking one more off. For magnesium, our first one's relatively big because that's taking us from magnesium to basically having our sodium ion or our sodium electron configuration. There's nothing really special about it. It's maybe a little bit more energy because we broke the pairing of the valence electrons. And then when we lose one more, we're going to the noble gas configuration neon, which is why it stays so low. We've just completed ripping off our valence shell. And then the third ionization energy, again, is huge because we're moving out of the noble gas configuration. We're taking an additional electron off. Another way that we could remember this is that there's a large ionization energy when the first core electron is removed. So, yeah. So here's our sodium. This is our 1s, 2s, 2p, 3s. This is the normal sodium electron configuration. And we've got, every time the number changes, right, our principal quantum number changes, we're adding on another shell. So for this 3s electron, taking off this one electron, we're just tearing off one electron out of the shell. There's nothing special about it, it's just one electron. And when we do that, now it's sodium plus. And notice that we've got a full shell inside of that. That's the noble gas configuration that I've been talking about. So we've got this full and complete shell. Everything's paired up, down. It's really stable to have everything filled. And so then when we go to remove this second one, we are breaking all of that pairing, all of that stability from having our electrons matched up. And that's why we get this extreme spike in ionization energy, because we're breaking that full shell. Does that clear anything up for you?
Well, I was just wondering, like why because unless I'm like misremembering, because I took a note of one of the last lectures that.
So lower energy means that it's more stable. Yeah. So the closer that we get to the nucleus, the more stable the electron is, and it's a negative energy. So we have to put in extra energy to remove those electrons because they're more stable, because they have lower energy.
Oh, lower energy as a negative. Oh.
Yeah, so these 1s electrons are very stable because we've got sodium, we've got 11 protons. There's a really strong force between our 1s electrons and our sodium. When we move to our 2s and our 2p, we're adding those outside. They've got lower effective nuclear charge because of the shielding of these 1s electrons, so they're not held quite as tightly. For our 3s is shielded by all of these. It's experiencing a Z effective of 1, an effective nuclear charge of 1 plus. So it's not held very tightly. When we bust into this next shell, our effective nuclear charge is now 8 or 9 because we've only got shielding from the 2 core electrons relative to these. So they're less shielded, they're less stabilized, or they're more stabilized because they experience that higher effective nuclear charge. So this is our trends in successive ionization energies. So on the top we've got first, second, third, fourth, all the way up to 7th ionization energy. And then we've got a bunch of different elements, sodium, magnesium, aluminum. So just moving across for our row 3. all the way out to argon. And our core electrons, or removing our core electrons, we can see those ionization energies in this shaded pink. So for sodium, when we lose our first electron, that's when it comes down to becoming that noble gas configuration. We've removed the valence shell. It's our last valence electron. And then we see a huge spike in ionization energy trying to break that core electron, remove that first core electron. For magnesium, it's a similar thing, but it's got 2 valence electrons. We see a huge spike in ionization energy when we remove the first core electron. Same idea for aluminum, but it's 1 later because we've got an extra electron. It's got 3 valence electrons, so it takes 4 to remove the first core electron, and so on and so forth. So removing core electrons is much higher ionization energy than valence electrons. So once you strip off that valence shell, then the ionization energy spikes. I think that would be the easy takeaway. You'll see a progressive increase as you get closer to taking off that complete valence shell. Once you've removed the entire valence shell, your ionization energy spikes, goes straight through the roof. And then you'll see another successive increase that's just kind of like normal size steps. And then if you take off that shell, I assume it would also spike again. On the other hand, we've got electron affinity. So electron affinity is basically the opposite, sort of the opposite of ionization energy. This is an energy change when an atom in the gas gains an electron. So this is basically the opposite of ionization energy. Just in terms of what's happening. For ionization energy, we put energy in to remove an electron. For electron affinity, we are gaining an electron, and there's an energy change associated with that. So energy is coming out instead of going in, an electron's being gained instead of being lost. Electron affinity is usually negative. We're releasing energy to gain an electron when an electron's gained, but it can be positive. So some alkaline earth metals and all noble gases have positive electron affinity. Any ideas why we might have that? Where are our alkaline earth metals? What do alkaline earth metals have in common with respect to their orbital diagrams or their electron configurations? They've got a full S shell. So our alkaline earth metals, they're going to have NS2, where N is just whatever row they're in. So they're going to have a full S2. And what about our noble gases? Noble gases have NS2, NP6. So they've got a full valence shell. So for those, when we add in another electron, we have to add it into added electron goes to the higher, goes to a higher energy orbital. Or subshell or shell. In the case of our alkaline earth metals, we're adding it into our NP, and P is higher energy than S. For our noble gases, we're adding it into a higher shell level. So we're adding it into the n+1 s. So in both cases, we're adding an electron into a much higher energy state. So our trends for electron affinity. Electron affinity decreases down group 1a. For our alkali metals, other groups don't show a trend. Electron affinity generally increases, becomes more negative across a period. So generally, this also increases up and to the left. And by increases, more energy released. There's some hiccups. So our group 5a has lower electron affinity than expected. So for nitrogen, we've got, for any of these 5a's, we're going to have our NP orbital diagram. If we add one in here, then it has to pair with one of these electrons, which is a little less favorable than just adding one in. 2a and 8a have very low electron affinity since the added electron goes into a higher energy level or sublevel, as we talked about on the previous slide. The highest electron affinity for any period is going to be halogens. Halogens like to pick up an electron to turn into their 1- ion. Fluoride likes to pick up an extra electron. If we look at electron affinities, we're looking at it increasing in terms of the negative numbers getting bigger. So for our beryllium and magnesium, it's greater than 0. You have to actually put energy in to add an electron in. And we also have positive values for all of our noble gases because we're adding a whole other shell of electron on top. So you have to put in energy to make that happen. Nitrogen also has a positive value because you have to pair up an electron. So some real quick orbital diagrams with the new electron in green. Sorry if you're red-green colorblind, I guess I'll change that to blue. Hopefully that's better. So all of that's not for helium. For the rest of the noble gases, though. And then the new one would go into the next row. You're adding a new loop shell, not very favorable. But generally, we can see our value increases as we move left to right. It's a little bit more wishy-washy, not as clear of a trend, but it does increase left to right, and it increases bottom to top. Questions about any of these fun, very cool trends? Okay. So some properties, comparisons, metals and nonmetals. Metals are malleable, meaning you can work them. They're a little bit bendy. They're also ductile, you can draw them into wires. Shiny, they're lustrous, they reflect light. They conduct heat and electricity, that's why we use them for wiring. Most oxides are basic and they're ionic. They form cations in solution. And they tend to lose electrons in reactions. They get oxidized. Losing electrons is oxidized. Nonmetals, on the other hand, tend to be brittle when they're in their solid state, Diamonds, you can't bend a diamond, it'll just break. They're dull, they tend to have non-reflective solid surfaces. Think graphite, which is the less crystalline version of diamond. They tend to be insulators. We don't use them for wires, on top of them being brittle. Most of their oxides are acidic, and they are molecular. And these tend to form anions and polyatomic anions, so negative charges. These gain electrons in reactions, which means that they are reduced. This quick reminder is just to jump us into metallic character, which I think is our last trend. So metallic character is just who's an ideal metal, who behaves most like a metal. How much of a metal is the element? And the big thing that we're thinking about here, the big thing that I think about here, is how easy is it to lose an electron? So metals like to lose electrons. We can also, if we just think about where are the metals on the periodic table, where are the nonmetals on the periodic table? Where are the nonmetals on our periodic table? They tend to live on the right side, things like fluorine, chlorine, oxygen, bromine, nonmetals. In contrast, our metals live on the left side of the periodic table. So it would make sense, I think it makes sense, right? Nonmetals are on the right side of the periodic table, metals are on the left side of the periodic table. So as you move left to right, you become more metallic. Sorry, my left to right, your right to left. So as you move from the right where the nonmetals live to the left, that's where the metals live. So it increases right to left. Metals are on the left and nonmetals are on the right. Metallic character also increases when you move down a column. So if we look at carbon and nitrogen, carbon is a nonmetal. If we move down that group, down that column, we've got things like tin and lead. And tin and lead are definitely metals. Carbon is a nonmetal. So as we move down, we're also increasing in metallic character. So this kind of just generally increases moving away from helium towards cesium. Here's some trends in atomic or in metallic character. Things like sodium, very soft metal. Chlorine is a gas. Sulfur is a solid. But we become more non-metallic as we move to the right. So metals on the left, nonmetals on the right. If we look at nitrogen, nitrogen's a gas. Phosphorus is kind of brittle, chunky. And then we get down to bismuth, and bismuth forms fun multicolored oxide crystals that have a rainbow effect on them. Bismuth is definitely a metal. You can melt it down. Relatively low temperatures too. So if you want to think of it as decreases left to right, increases top to bottom, that works. But again, increases in these directions. Because metals are on the left, nonmetals are on the right. Based on our periodic trends, please choose the more metallic element from each pair. I'll give you some time to do that. Go ahead and highlight in those pairs. All right, some comparisons. Our first one, we're comparing germanium and tin. Which is more metallic? Tin is more metallic. Tin is a metal. It's lower and in the same group, so it's more metallic. What about gallium or tin? Which one's more metallic? So this one we have competing trends. So gallium is further left-right. It increases right to left. Tin is lower top to bottom. So gallium wins on one trend, tin wins on the other trend. So for this one, it's unclear. I would guess it's probably tin, but I can't be 100% sure about that. And then phosphorus or bismuth. Yep, definitely bismuth. Bismuth is lower in the same group, and so it's definitely more metallic. And then last but not least, boron or nitrogen. Yeah, this one's boron. It's further left. And metals live on the left side of the periodic table. Non-metals live on the right side of the periodic table. For that trend at least, left to right, right to left. Questions about any of those? Okay, a summary of our periodic trends. We talked about atomic radius, first ionization energy, electron affinity, metallic character. There's not a super clear electron affinity trend for moving down a column. For the other ones there was, and we did have a trend for electron affinity moving across a row. So as we're moving down a column, atomic radius increases. So atomic radius increases down. And for atomic radius, when we move across a row, when we move left to right, we're increasing effective nuclear charge, and so that causes the valence electrons to suck in a little bit. Let me do these increasing ones in green. So atomic radius increases when we go down. It also increases as we move right to left. First ionization energy, as we move down a column, decreases. Because our outermost electrons are further from the nucleus, they're easier to remove. So ionization energy increases as you move up because the atomic size decreases. The electrons are closer to the nucleus. For first ionization energy, it also increases as you move left to right. And this is because of effective nuclear charge increasing. For electron affinity, this is arguably becoming the most confusing slide. I'll rewrite these on the blank slide. But as you move left to right, electron affinity decreases because of that effective nuclear charge increasing. For metallic character, it increases as you go down. Thank you for these very helpful arrows. And it also decreases as you move left to right, which means that it increases right to left. So atomic radius, our trend, increases down and to the left. Ionization energy, first ionization energy, not second or third or fourth. Increases as you move towards helium. electron affinity decreases as you move left to right. There was not a clear trend top and bottom. So electron affinity is going to be higher on the left, which I think means less negative. And then metallic character also increases as you move down and to the left. So we've got 3 trends that increase right to left and top to bottom. We've got 1 trend that increases bottom to top and left to right. Questions about any of those? Okay, then we'll stop there.